Hey there everybody. In this video we're going to keep going in chapter 6, and what you might notice here is that this section number has a star on it. If you're following along in the ebook, the way the book is laid out is the book goes 6.1, 6.2, 6.3, 6.4, but then there's a 6.2 star, 6.3 star, 6.4 star. We do the star sections. So if you're flipping through the ebook trying to figure out what's going on, make sure you're flipping to the right ebook sections, or the material won't line up and none of the exercises will make sense. So the book is designed to teach the material in two different ways. We use the star method. So they're like a blue, the pages are like a blue tint. So let's jump in. So chapter 6 is all about natural logs, regular logs, logs base b, exponentials, and the e function. Also, there's some inverse trig functions and some other stuff coming later that we're going to see here in a little bit, in a few sections away. So the first thing we do is define the natural log function. And it's ln of x, right? You guys have seen this before, but the way that it's normally defined is that ln of x is the inverse of e to the x. And without calculus, it's actually hard to define either one of those things. With calculus, this is our definition. We just say it's the integral of 1 over t dt from 1 to x for positive numbers, for positive x. And then we just invoke the fundamental theorem of calculus part 1, and we get the derivative of natural log x because of how this works. Remember, when you have the derivative of a to x f of t dt, you just replace t with x. Okay, so we're defining this thing in such a way that its derivative is 1 over x. So we're saying whatever this function is, its derivative is 1 over x, because its antiderivative, as defined here, is the function itself. So I'm not going to spend a ton of time on this definition, but it is important that you understand it. That here's 1 over t. So the area from 1 to x is ln of x. That's if x is greater than 1. And if x is less than 1, we actually define it as the negative of the area. The reason that is because of the definition. Go back and look at it here. If x is between 0 and 1, then we're going from 1 to 0, so we're putting a minus sign out front. Remember, that's the same thing as switching the bounds and getting rid of the negative, right? So that's all we're saying. We're just saying that if you head to the left from 1, that the area becomes negative, right? So so the area itself is negative, but the natural log function is the negative of that area. We just put a minus sign in front of it. Here's some properties. These are called natural log laws. These work for all logs, but we're really just focused on the natural log today. So if you have multiplication inside a natural log, you can distribute the natural log and it becomes a plus sign. If you have division, you distribute the natural log, it becomes a minus sign. And this is the one we're going to use the most for sure. If you have a power, you can pull the power to the front of the natural log. By far the most useful property in calculus. So let's see how to do this. So we want to expand this into a bunch of natural logs, right? So the first thing we do is you say, well, I see a division sign here. So this is going to be positive. This is in a denominator, so it's going to be negative. So you just distribute the natural log, and then anything in a denominator gets a negative sign. Anything in a numerator gets a positive sign. Now you can see that we have all of these exponents. We pull all those to the front, and that's your answer. So a lot of you guys probably remember this stuff. If you forgot it, again, it is a little bit of a algebra review. I don't do a ton of algebra review, That's why earlier in the class I did 2 different algebra reviews, just because of this kind of stuff. Because now we already have all of our derivative and integral rules. That you have to keep track of those while recalling these natural log rules that you might not have seen for a while. So here's the opposite of that previous question. We're going to use the laws of logarithms now to compress this and simplify the answer as much as we can. You're going to want to pay special attention to when a problem says simplify or don't simplify in chapter 6. Well, before we move to the solution, let's see what's going to go on here. So we have a 1/3. So we're trying to compress this into a single log. So any exponents, do the exponents first. So anytime, if there's exponents here, so here there's a 2. But what we want to look at is we have these constants out front that can become exponents. We're going to push this 1/3 up here. We're going to push this 1/2 up here. So that's what I did in the first step. So we're trying to compress this thing together. The next thing I want to do is simplify if possible. This 3 and this 1/3 will cancel. I can't distribute this 1/2 in here, but I can combine this. Now that I have a minus sign, I can combine these two together with a division symbol. So over here, the 3 and the 1/3 cancel. Here, the 1/2 is still on the outside, the power, but this minus sign has become a division symbol. Now that we have division, I can distribute this 1/2 inside, and that's what we do next. So here, x to the 1/2, and then anything squared to the 1/2 power, those cancel. Now we have a sum, so that becomes multiplication, right? So this x plus 2 gets pushed inside, and then I factored this denominator, because you're trying to get stuff to cancel. Whenever you're dealing with natural logs, you always want to simplify, 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 and factor. If you see natural log, stuff will cancel all the time. Well, this x plus 2 and this one are going to cancel, and it actually simplifies really, really nice. So look what it started off as, and look where it ended up, right? It's unexpected. This happens a lot, so make sure you're simplifying inside natural logs or whenever you have lots of natural logs. All right, well, let's keep going. Here's just some facts about the natural log function. So it's increasing, it's continuous, domain 0 to infinity, range -infinity to infinity, and it has these 2 limits, right? So as x goes to infinity, the natural log of x just keeps growing, and as natural log of x goes to 0 from the positive side, remember, it's not defined on the negative side, it goes to -infinity. And so natural log of x is continuous. I want you guys to think about why it's continuous. I'm not going to tell you the answer. But I do want you to have some deeper thoughts about this stuff. So ln of x is continuous. It takes on each real number value for some x equals c on its domain, right? So think about it, right? It's continuous. So every number in its domain has to have some x value that gives you that number back. Could be more than one. So what we do is we know the derivative of natural log x is 1 over x. That was given earlier. This shows us that the graph of y equals natural log x is increasing everywhere, and it's 1 to 1. So let's talk about this a little bit. It's increasing everywhere because this is always positive. Remember, x is always positive. You're not allowed to put negative numbers in a natural log. This is always positive, so it's always increasing. If it's always increasing and it's continuous, that means it passes the horizontal line test. That makes it 1 to 1, and if it's 1 to 1, it has an inverse, right? So let's look at the second derivative here, right? That's the most important one. This is just a copy of the previous slide. So this is saying, so we know the first derivative, and then the second derivative, you guys know how to do derivatives of 1 over x. So it's -1 over x squared. This tells us, so this is always negative. That means the graph is concave down. and there's only one value c where natural log of c equals 1. So this tells us increasing everywhere 1 to 1. When it's concave down, that should make sense, right? So the graph kind of comes up like this. So there's only one number where the natural log of c equals 1. That's a really fancy number. It's called e. It's the only number that you guys will see in math that gets a English letter, like a Roman letter, E, instead of a Greek letter. And we're going to use this number a lot. So this is an irrational number. It never repeats. And this fella, Leonhard Euler, he has two numbers named after him. So E is named after him. And he also has this other one called Euler's gamma. If you guys are big math fans, you can look into that. It's a pretty interesting number. It pops up a lot in science. E pops up absolutely all the time. So I'm going to give you guys a quick note about this word transcendental. It pops up all the time. A lot of calculus textbooks will say things like early transcendentals, late transcendentals. Our textbook doesn't say anything about transcendentals. Here's our book. Look at that thing. But what it is our book does a mixed approach, early and late transcendentals. So essentially a transcendental number is a special kind of irrational number that not only does not repeat, but it fails to repeat in a certain way. So numbers like pi and e are transcendental, but square root of 2 is not. And many functions, so trig functions and logarithms, are called transcendental functions because they commonly produce transcendental numbers as outputs. So if you guys have seen this transcendental functions or early transcendentals, that's what this is referring to. So some textbooks introduce natural log of x and e and trig functions really early. Now we do it later. We defined the definite integral first because we use the definite integral to define natural log of x and e to the x. Other textbooks will define e to the x using just properties of derivatives. And again, our textbook takes a mixed approach. Trig functions come early, and other transcendental functions are here in chapter 6. All right, so we've seen that the derivative of natural log of x is 1 over x. But of course, there's always a chain rule. So what happens if we have a chain rule? So if you're taking the derivative of natural log of u, it's just 1 over u du dx. Or if you want to call it natural log of g of x, then it's just g prime of x over gx. So just the way where this comes from is that it's just 1 over this times the derivative of this. Well, we can just pop that in the numerator. So you don't have to remember this as a separate formula, but you do have to remember the chain rule. All right, so here we have an example that is a composition of several log functions. So our function is natural log of x squared minus 9x. So we're going to find the domain. We're going to find the limit as x approaches 9 from the positive side. And then we're going to find the derivative. So lots and lots of stuff going on here. So let's jump right in. So we're asking about the domain of natural log of x squared minus 9x. But let's look at the domain of natural log of x first. So natural log of any function has to be between 0 and infinity. So what we have to do is solve x squared minus 9x. We want to find where that thing is greater than 0. Because that's what's sitting inside the natural log. So we need to know where is the input of this inside function greater than 0. So you solve it using the standard rules of solving inequalities. You factor and set it equal to 0. This tells us that that the function is exactly 0 when x equals 0 or x equals 9. And we want to know what values of x will become positive because we need positive numbers as our input. So you just either make a sign diagram or use test values. So you can see what's going on here. These are where this function is 0, or the factored version is 0. So remember, these zeros break up the inequalities into several regions, right? We have negative infinity to 0, 0 to 9, and 9 to infinity. So we want to know which of those three regions is positive. So I just grabbed some test values. So -1 represents everything less than 0. 1 is just a number between 0 and 9, and 10 is a number bigger than 9. I just plugged everything in, and I found that the function was positive with the test values -1 and 10. So that tells me that the domain is negative infinity to 0 and 9 to infinity, because this test value is in this region and is positive. This test value 10 is in this region and is positive. The one, when I plugged in 1, I got a negative number. Negative numbers cannot be inputs, so that's not part of the domain. And this is a pretty interesting function. So let me show you the graph of this function here. It's pretty interesting, and I'm doing it on my calculator. So nothing fancy going on here. Okay, let me see if you guys can see this. Right, so it's a pretty strange looking function, right? And you might think, but I mean the domain matches, right? You can see that there's this big gap in the middle. So you might think that when we want to find the limits, you might think, so the next question is, what's the limit as x approaches 9 from the positive side? So what does it look like that limit's going to be? So 9 is way over here, right? 9's over here. What does it look like that limit's going to be? So you'll probably say it looks like the limit is 0. Let's do our math and see if that's true. All right, so that's what we're trying to find out, right? We're trying to find out what's the limit of the natural log of this function as we come in from the left side. So what we can do is, we're assuming this limit exists, so we can bring the limit inside the natural log. Remember, if it's infinity or negative infinity, those counts as limits existing, right? We just have to make sure it's not division by 0 or DNE, right? So I just pulled the limit inside. So what is this limit? Right? Well, that limit's 0. Again, from the positive side. I know that's hard to see, but it is. Because x squared is always bigger than 9 times x. So this is coming in from the correct side, positive. And again, this is a continuous function. You can just plug in 9, but again, we need it to be coming in from the right side. So if you plugged in like 9.1, this would be a positive number, right? If you plug in 9.01, right, this would be a positive number. So that's how that works. But look here, this is telling us this is 0. If this is 0, natural log of 0, so the limit as we come in, right, that means this thing is negative infinity, but that's not what the graph looks like. So what is going on here? Why does the graph show us that this thing's 0, but it's not? So to answer that question, I want to show you what it looks like when we type this into a table. All right, so here's a few values. 0.00001. Here we go. So look at what I did here. 9.1, it's negative. 9.01 is negative. Right? So what exactly is going on here? Well, what's going on is that your calculator does not have the resolution to draw this thing properly. So if you're just looking at it, the calculator only calculates in increments of like 0.1, and then it just connects everything. You've got to use what you know. So just type in some numbers. You can see this thing's going negative, and there's no limit. Right? The closer that this thing gets to 0, that this limit is eventually going to become negative infinity. So you can just keep typing in numbers closer and closer to 9, which causes that whole limit to be closer and closer to 0, which causes this thing to go to negative infinity. So that's a tricky problem. Don't just draw graphs, guys. So if this is a test question, you've really got to show something very similar to this. And last one, the derivative. So here I'm just using the rule, and I'm showing you with the chain rule. So the derivative of natural log of anything is just 1 over that thing times the derivative. That simplifies real nice, and you're done. So derivatives really aren't too bad with this stuff. But it is a whole new set of rules, right? None of these rules look like things you've seen before. All right, well, that's a really busy page. Let's keep going. All right, here's another one. We're going to find the derivative and second derivative of natural log of secant x plus tangent x. And I gave you a nice little purple message at the bottom. Remember these formulas. Let's see what happens. All right, so we just take the derivative of both sides. On the right side, you can see that we're going to have that natural log rule with the chain rule. Right? And so here I just simplified it as g prime of x over g of x. I'm just using that formula from earlier. It saves a little space. So we go ahead and find that derivative on top. And you might be tempted to stop here. But as you've seen before, anytime you have trig, just nothing but trig functions, keep simplifying, stuff might drop out. So what did I do here? So this is something that I wanted to point out because a lot of people have been missing it on exams. When I say simplify, it doesn't mean to distribute all terms. It means factor terms and then attempt to cancel. So here there's a secant and a secant squared. So you factor a secant out, right? So now we have a secant x plus tangent x. Well, that cancels. Secant x, you're done. So this might be a really surprising result. But it turns out that this is the only way for us to find the integral of secant x is to experiment with derivatives. And now that we have natural logs have a lot of nice properties when we take the derivative. It puts the derivative on top of the original function. And with trig functions, a lot of stuff will cancel. Well, if that's y prime, we know what the second derivative would be. It's just the derivative of secant x, so that one's real easy too. So this is a really nice proof. And remember, this formula moving forward is very important because we've proven that the derivative of natural log of secant x plus tangent x is secant x. That means the integral of secant x is this. Well, is this, right? So it's hard to prove going backwards, right? You can see like u substitution isn't good enough going up. So if we had to do an integral, so just make sure you can do this derivative. Okay, next up, we're going to actually, this is a slight variation on what we just did. I'm claiming that the derivative of natural log of absolute value of x is 1 over x. We've already seen that the derivative of natural log of x is 1 over x. Here I'm saying that the derivative of the absolute value of x. That also means that the integral of 1 over x is natural log of absolute value of x. So before we go any further, let me point out why this is important. Number one, the domain of 1 over x is everything except 0. So if we just said to ourselves, the integral of 1 over x dx is natural log of x, natural log of x, the argument, the x is not allowed to be negative, but it is allowed to be negative over here. And one thing you're going to see as we do more and more derivatives and integrals, and there's plenty more to go in this class, is that when you take an integral, the domain won't change. When you take a derivative, it might change. Right? There are functions that are continuous but not differentiable in certain spots. But if a function is continuous, it can be integrated everywhere. So you don't want the domain to change when you integrate. So the domain here is everything except 0. So we want the domain of its integral to be everything except 0. And it turns out these formulas rely only on properties of derivatives. So here's the proof. And proving the derivative will prove the integral, the reverse direction. So by definition, natural log of absolute value of x is just ln of x if x is positive, and ln of minus x if x is negative. Remember, it's not allowed to be 0. So what we're going to do is take the derivative of this and this. And we're going to show that both derivatives give you the same answer. So the derivative of natural log of x is 1 over x. That's how we started off this section. Of course, that's true. But what about the derivative of natural log of minus x? What happens here? So it's 1 over minus x times the derivative of minus x. The derivative of minus x is minus 1. The negatives cancel, and you get 1 over x. So these two different functions have the same derivative. And so that's important. And if you think about it, this should make sense. If I were to take the integral of 1 over x, you just get natural log of x plus c. C is allowed to be any number, right? So think about that. So when you have a natural log and you add c, c is just natural log of some other number, which is just, so you have ln of x plus ln of, just some other number, Well, you can combine those and make a natural log of c times x. So depending on what you want c to be, it turns out that any constant here will give you the same derivative. And we'll see that later. All right, let's do an integral. So you look at this and you say, all right, how do I do this integral? Does this look like something on your integral sheet? It doesn't. Right, all we have is integral of 1 over x now. We have our power rule, we have trig functions, and that's it. We don't know the integral of natural log of x. So what we have to do is a u substitution. So you look for the most inside function. So natural log of x is inside this fourth power, so that qualifies as an inside function. So let's make that u. That means du is 1 over x. And then all we have to do is rearrange this to get it to look right. So here, I just took the 1 over x out and moved it over here next to the dx. So this is going to be u to the fourth. This whole thing is du. I know how to do this integral. This is 1/5 u to the fifth plus c, which is, and then you just bring u back in, which is natural log of x. So we just get 1/5 natural log of x to the fifth plus c. So this is just a little window ahead into what we're moving into, this kind of stuff. For most of the stuff you're going to see in chapter 6, it's a lot of sort of quick problems like this. You should be able to work through a problem like this on your own in 2 or 3 minutes, maximum. All right, let's do another one. All right, integral of tangent x. So we just saw the integral of secant x earlier, right? Because we found the derivative of that other thing. So you're looking at this and you say, how the heck can I do integral of tangent x? Well, you just got to be clever, right? Because you need to look for things that have derivatives of something else. So you have to turn one function into 2 functions. Well, here's a good way to do it. Now that we have 2 functions, is one of those things the derivative of the other? Well, they're both the derivatives of each other. So how do you know what to pick for u and what to pick for du? So the way to do it is look at this denominator and say, I want that thing to be u, because when I do a du, the derivative will appear in the numerator. Taking a derivative can't put a function in a denominator, but it can put a function in a numerator. So that's what we're going to do. We're going to say u is cosine x, so du is negative sine x dx, and we're going to fiddle with it until it, matches up. So the integral of sine x over cosine x dx, I just moved it around so it looks better. So this whole thing is 1 over u. This whole thing is negative du. I'm going to pull the negative out front. Now I'm ready to do an integral. So this is just negative natural log of the absolute value of u plus c. Now we plug u back in, get negative natural log of cosine x plus c. Again, notice that we need the absolute value here. That's the rule. Are we done? Or do we need to simplify? Technically, you could stop here, but it's not all the way simplified. I would recommend continuing on to get it in a slightly more compact form. Because you have a negative out front of a natural log, you're allowed to bring that exponent inside. Simplify it. 1 over absolute value of cosine x is absolute value of secant x. So this is the natural log of the absolute value of secant x plus c. And this is the answer. This isn't wrong. It's just not all the way simplified. So on a test, this would be fine. But on the homework, it might want you to simplify it if you have a problem like this. And it's same stuff we talked about earlier. Remember when I said way earlier in the class that the derivative of secant and tangent always is made of secants and tangents, just in some configuration. And that's what we've seen here, right? The integral of tangent contains only secants, right? I mean, it's a natural log also. And with the integral of secant was the natural log of secant x plus tangent x. All right, let's keep rolling. Last thing we got today is logarithmic differentiation. This is a special technique. It's a very powerful one-size-fits-all technique. And what it lets us do is simplify really complicated derivatives using laws of logarithms. So the way we do it is take the natural log of both sides of some function and then simplify using laws of logs. Just expand everything as big as it'll go. Because when we take derivatives, we don't want to use the product rule. We don't want to use the quotient rule. We'd rather just use pluses, right, and constants. Step 2, you differentiate, and then you solve for y prime. So it's a very powerful technique. You're actually allowed to use it whenever you want, and it works. So if you see a problem earlier from chapter 2, and you're like, I don't want to use the quotient rule, I want to use logarithmic differentiation, it's fine. It always works. So look at this monster. We know how to do this. This would be a product rule and quotient rule and double chain rule, right? There'd be a chain rule under here and a chain rule in here. So do we want to do a product rule, quotient rule, chain rule, chain rule? I'd rather not do that. So what we do is we take the natural log of both sides. Then I'm going to use properties of logarithms to simplify the right side. Here, anything that's multiplied becomes a plus and the natural log distributed. Anything that's a minus, anything that's in a denominator is a minus. These all have exponents. We're going to bring all those exponents out front. And now just looking at this, you can't get rid of the chain rule. There's always going to be a chain rule, but it's much easier to do a natural log chain rule than a bigger, more complicated chain rule with the quotient rule and stuff. Let's go ahead and take a derivative. So I just put primes on it, big old derivative. So the left side just becomes y prime over y. Here this is, and I always pull constants at the front, so just get used to that. Derivative of ln of x is 1 over x. The 1/2 stays out front, so the derivative here is 1 over x squared plus 1 times the derivative of x squared plus 1. So again, just put it, just to keep it compact, just stack that derivative in the top. And I did the same thing here. Pull the constant out front, derivative of the natural log goes in the bottom. I'm sorry, the inside function goes in the bottom, the derivative goes on top. Simplify everything. And here, so I simplified everything on the right, and then I multiplied this y back over. And then plug y back in. So I just simplified everything. So you can see what happened. I canceled these 2's, and I multiplied this 5 times 3 out. I did not attempt to further simplify. You can imagine how horrible this would be to simplify out. Please don't do it. If you want to simplify little things like 2 divided by 2, I would recommend that. 5 times 3, we know that's 15, just write it as 15. But don't try to simplify these really complicated expressions. Even if something were to drop out, it's probably still not worth the amount of effort you have to put in. So to get this thing all the way simplified would take another 5 or 6 steps of algebra. Forget it, it's not worth it, leave it like this. All right, well that's it for this section. If you guys have questions, post on the discussion forum or send me an email. And I'll see you guys next video. Bye-bye now.